Yeah, so the point of this talk is to see the invisible. It's an ambiguous term, what invisible is, many things could be, with black hole superradiance source gravitational waves. So before getting into what the invisible is and exactly what I'm trying to do here, I would like to talk about how superradiance works, because since now a lot of things have been talked about apart from superradiance. So I'll just briefly touch superradiance and how black hole superradiance would work. So yeah, so let's assume these are rotating cylinders and you are watching them from a head-on perspective. Okay, it's rotating like this, and you have some sort of a solid ball which will come and scatter with the cylinder. And cylinder has some sort of frictional outer layer. Okay, it has some sort of absorption or dissipation going on. In that particular case, you would expect that due to the scattering, there will be some energy loss of this ball and it would slow down. Now, that is one way of looking at it. However, under special circumstance, if you think that this is also rotating in this direction and this rotational velocity is higher than the translational velocity of this ball here, then it can speed up the ball at the expense of its own energy, rotational energy. So essentially, this is the classical analog of superradiance. When we have a larger rotating object and a smaller object which has a velocity lower than the rotating object, then at the expense of the rotating objects, like larger rotating objects, rotational energy, the smaller object can speed up. Okay, so this is like object particle perspective. You can look at it from the wave perspective as well. So what happens from the wave perspective, as opposed to the increase in velocity, the amplitude of it can increase. Right, now in the quantum field theoretic perspective, if the amplitude is increasing, right, so in that particular perspective you can think of it like more quanta of particle is being generated. So initially, even if there were less number of particles, more number of particles can generate from the superradiance itself at the expense of this object's rotational energy. Now the point is, thankfully in nature, we have objects like this, which is rotating and which has an absorptive outer layer, which are nothing but the curved black holes. So curved black holes are objects which are rotating. It can rotate slowly or pretty fast. And it has obviously the event horizon. Or for a curved black hole, it could have multiple regions of horizon and stuff like that. But all of them can have some sort of dissipative effect. And as a result, what we can think of is that if there is an incoming wave through the scattering with this dissipative outer layer of the curved black hole, we can have there is some sort of enhancement of the amplitude of this wave. Now the point is, this enhancement is happening, but it's not very efficient if the wave just comes, gets enhanced, and then goes. So okay, in that case, we need many of such waves to extract an significant amount of angular momentum, because black hole is humongous. You can think of it as a humongous object as opposed to one single wave. So then how to do that? Thankfully, nature has a way to do that as well. If you think of a massive particle or a wave, which describes a massive particle revolving around curved black hole, then large enough distance away from the black holes, like from the black hole, you can think of it as this kind of a potential, where mu is the mass of the particle, mh is the mass of the black hole. And then the potential looks like this, and as a result, what happens? It gets trapped in between. It just goes back and forth. And every time it passes the object, it amplifies. So eventually, it is many repeated amplification. And as a result, the efficiency of the process of angular momentum extraction through superradiance becomes very large. But that also creates some sort of a instability, because if one wave or something keeps on extracting energy from a rotating object, then one thing is for sure, the rotating object has to lose a lot of rotational velocity. And after a certain point, it has to be in a certain position where it cannot give away energy anymore, which we'll see in the next slides. The point is, if you think of this system, a black hole in between and some sort of bosonic states, let's say, we have to have these bosons, otherwise I'll come to that, why we need bosons. But if you have something like that, then this potential is very familiar to us. Essentially, this looks like the hydrogen atom potential, right? So this is the gravitational fine structure constant, this Gm mu thing. And obviously, dimensionally, it is not correct. You have to, in denominator, you have to put a h bar and c, and then Gm mu upon h bar c is my gravitational fine structure constant. So this problem will look very much like the hydrogen atom problem, and with the energy states of this bound system will be characterized with, just like the hydrogen atom, n, l, and m. Okay. So the cloud size so what essentially is happening, that if we have quantum mechanical fluctuations, we do not need physical particles for this amplification. Even if you just include this particular bosonic field in the Lagrangian of the universe, there will be quantum mechanical fluctuations around this black hole, which is good enough to start the energy extraction process. And once the energy extraction process starts, the cloud will grow. Till when it will grow, I'll come to that, but it starts growing. So without even an existence even of a single massive particle, through quantum fluctuations, these massive particles can just appear and they can extract energy from this black hole and create a cloud. The cloud size is something of this sort. Now, this alpha is the gravitational fine structure constant, and it will be seen that this alpha, like the superradiance process, is very much, let's say, efficient when the alpha is somewhere from 0.01 to 0.5, somewhere around that. So the alpha is much smaller than n, obviously, and as a result, the cloud is much larger than the radius. So at the edge of the cloud, we can actually, relax some of our general relativistic calculations, and that's why the potential that I took could be taken. We do not have to necessarily do very complicated GR calculations. We can take Newtonian approximation at the faraway region of the cloud. And if we look at a one particle energy, then obviously the first term is just the rest mass of the particle itself. The second term is sort of like a binding energy of the gravitationally bound object. And the third, the imaginary part, is the rate of superradiance, how well the particles are extracting energy and going to different states, right? And since we have the I here, that's why the enhancement happens. So as a result, what is happening here is this particular thing will give us that how well the energy extraction happens and how well the cloud different energy levels will have their energies. So the superradiance rate, which is this, most efficient as at L equals m value. So the most efficient ones will be, let's say, 211 or 311, or let's say 322, 422, things like that. And furthermore, 211, as the n value is lower, the superradiance rate is much, much higher. Okay? To depict it further, we can look at something like this. So this one, if you look at, the y-axis is the spin of the black hole. It's a dimensionless spin, if you really think about it. So basically, angular momentum upon g time m squared. It's a dimensionless spin. For 0, it is a Schwarzschild black hole. For 1, it's an extremal curve. Okay? And this is the alpha, the gravitational fine structure constant. It can be expressed like this. So you can think about it like that. If we have a particle, a bosonic particle of mass 7 times 10 power minus 19 GeV, with the mass of the black hole as 1 solar mass, the alpha would be of the order of 0.005. So let's look at this. If a gravitational atom, the structure, the cloud with the black hole is called gravitational atom. So if a gravitational atom is initially at A, as you can see, it is within the regime of L equal 1 superradiance, right? So what happens is the energy, the particles actually start extracting energy, more precisely angular momentum. And the black hole's spin actually reduces. And after a while, it reaches a point B. Now, as you can see, is not, the spin of the black hole is not high enough for L equals 1 superradiance anymore. But we can still have L equals 2 superradiance. So now the L equals 2 superradiance starts and the angular momentum extraction happens at a much lower rate. And eventually, when it reaches the point C, it is out of the superradiant regime. So no more superradiance can happen. However, this TAB, for the amount of time the black hole takes to come from point A to point B, is much, much less than it takes from coming to point B and C. And by much less, I mean much, much less. In order to illustrate that, you can think about a system which has a gravitational fine structure constant of 0.2, and the particle mass is of the order of this, 6 times 10 power minus 22 GeV. So then coming from A to B will take 1 year, and coming from B to C will take 10 power 6 years. And that essentially shows us how much more efficient L equal 1 superradiance regime is than L equals 2 superradiant regime. Okay? So now gravitational wave generation. We have talked about superradiance and how gravitational waves can be generated from this kind of a system, a gravitational atom. There are two different ways. One is the annihilation of scalars. Suppose the 211 level, or any level for that matter, is filled with a lot of bosons. Now what can happen is they can annihilate into gravitons. Okay? Or transition of energy levels can happen. Suppose we have a 211 level and a 311 level. So particles can come from 311 to 211 and gravitational waves can be extracted. So in this one, gravitational wave frequency is just of the order of 2 times the particle mass. In my paper, the one I'll be talking about, we have considered this, so I have given details of this. However, this one can easily be treated in a similar fashion. So here I talk about the transition from 311 to 211. Since the L equals 1 is the most dominant superradiance level, you can also think about transitions from 422 to 322 and things like that. However, they will not be as dominating as this as long as this is happening. So we consider this one. Now the energy level transition, the difference between these two energy levels can be expressed like this as a function of the point structure constant and the particle mass. Furthermore, this tau GW is for how long, for a transition like this, the gravitational waves will be, the gravitational radiation will go on till, it is not efficient anymore. The transition is not efficient anymore. And you can see that for a particle of 10 power minus 21 GeV mass and for a black hole of 20 solar mass, it is approximately 6 months. Okay, but it has humongous dependence on these things. And finally, the energy that is released in the form of gravitational waves can be expressed in the form of that. Okay. Now with this, I come to the main scheme of what I want to talk about. Let's say in early universe, some A happens. Okay, and theory predicts that there will be something which is observable from this A and something which is slightly invisible, difficult to observe. In that particular case, we can have another difficult to observe thing combined with the difficult to observe first thing, giving a simply observable thing. Okay, a bit difficult, but in our paper, what we consider is first order phase transition as A. It obviously predicts stochastic gravitational background. And since it's my favorite, it also can predict primordial black holes in some sense. However, we might not be able to see the primordial black holes as easily as we might be able to see the stochastic gravitational background. But then in presence of ultralight scalar, these primordial black holes, as I have mentioned in the previous slides, can create secondary stochastic gravitational backgrounds. And the whole idea is to see the interplay between them solely based on the FOPT parameters. Okay, so we have had many talks about first order phase transitions, so I'm not really getting into the details of that. But the parameters, okay, this is a different alpha than the alpha I was talking about. I should have used different symbol, but I'm sorry about it. So this is also another alpha, which actually talks about the strength of the first order phase transition. And then we have a beta upon h, which talks about the inverse duration as a ratio with the Hubble time. And then we have the reheating temperature, we have the bubble wall velocity, we can have other things also, but I have kept a dot because Professor Constantine will be talking about them tomorrow, which is the energy budget things. But essentially what we can think about is that depending on alpha, beta upon h, and let's say the temperature, reheating temperature, I should have written reheating here, we can model the gravitational wave spectra. Okay? The peak frequency of the gravitational wave, stochastic gravitational wave due to a first order phase transition, depends only on the reheating temperature during the first order phase transition and the beta upon h. The next thing is the primordial black holes. Now, primordial black holes from a first order phase transition can happen in a few different ways. Like one way, Francesco already talked about this actually in his talk. So collapse of overdense regions. Since the bubble nucleation is a probabilistic process, we might have some Hubble patches where the decay of false vacuum happens a bit late. And as a result, overdense regions can generate, which might collapse upon themselves to create primordial black holes. This is one way. There are a few papers on that. Another way is, same idea, but let's say you have different Hubble patches and the vacuum energy is actually decaying, like the vacuum, the false vacuum is decaying in different times at these different Hubble patches. As a result, there will be a time fluctuation between these different regions. So we can have a curvature perturbation, super horizon curvature perturbation. And these curvature perturbations then can enter the horizon and collapse if they're large enough to create primordial black holes. In this paper, I talk about the first one. So this paper by Gotner and Volansky, which was referred by Francesco as well. So here, this peak goal actually talks about the probability of collision, a probability of collapse of a Hubble patch, which essentially depends on just beta upon h and the delta C. Delta C is the threshold. What should be the density contrast so that a region can collapse into a primordial black hole? How much time do I have? Okay, I have been very fast. So now I'm going to be slow. This is the abundance. So in the collapse probability, the abundance is actually directly related to the collapse probability of collapse and the temperature of reheating. This is due to the fact that let's assume the same collapse probability happens in a very early universe and a bit later universe, and the primordial black holes have formed. But then it depends that how much of the universe actually have been collapsed, and this FPBH is today. FPBH is essentially the ratio of the density parameter of the primordial black holes upon the density parameter of the dark matter, whole dark matter. So that's why it has a temperature dependence as well. And finally, the mass of the primordial, okay, I have made a mistake here. Finally, the mass of the primordial black hole depends on the reheating temperature, the degrees of freedom, I should have written a m solar here. So this is this thing times this thing times m solar. So essentially, just like the previous one, where we could, talk about the entire gravitational wave spectra using beta upon h and temperature mostly. Here also, we can talk about most of the properties of the primordial black holes created from the first order phase transitions using the reheating temperature and the beta upon h. So this is the observables from the first order phase transition. Now we go to the stochastic gravitational background due to black hole superradiance. Now, as I have mentioned initially, okay, this is too loud. As I have mentioned initially, the primordial black holes, which will take part in the superradiance, have to have large spin. Otherwise, the superradiance process will not be efficient. But we have a paper where we have shown that primordial black holes created from first order phase transitions in radiation-dominated universe will have very low initial spin. So then what to do? Thankfully, we have a situation for that as well. We consider merger remnants. If two initially non-rotating black holes merge, then the remnant of them, the final black hole, after merger, will have a spin of 0.7, of the order of 0.7, 0.68, 0.7. So then what we do is, in order to calculate this superradiance, stochastic gravitational background due to superradiance from the merger remnants of the primordial black holes, we have this equation. But this one, basically, Fs is the frequency of these gravitational waves at the source frame. And this peak I basically talks about the distribution of the black holes, which will take part in the superradiance, and distribution of their spin. Since we are only talking about merger remnants, we can safely take it that all the black holes which will be taking part in the merger will depend on, will have a spin of 0.7. And then this tau is actually the rate, the event rate of the mergers, which can be expressed such as this. Now the issue here, unlike last time, here, till this point, you don't see any temperature dependence. The temperature dependence will, like reheating temperature dependence. The reheating temperature dependence here will enter through the M1 and M2. So here the M1 and M2 are the masses of the two black holes which will merge. Now here we are considering these black holes to be the black holes we created from the first order phase transition itself. And as a result, the temperature dependence will enter here. And here, this F you see, this F is essentially the mass function. Or for a monochromatic case, we can think about this as the abundance of the primordial, or abundance of the black holes which will be taking part in this merger. And this, as we have seen in the previous slide, depends on temperature and beta upon h. So this one also indirectly depends only on the reheating temperature of the first order phase transition and the beta upon h of the first order phase transition. So now let's look at the two components of the stochastic gravitational background. Now we have talked about the two components, right? One is the first order phase transition, and the other one is from superradiance. Now, one interesting thing is I have plotted the peak frequencies here of these two signals as a function of the reheating temperature. Okay, as you can see, the superradiance one depends, it has a t-squared behavior, whereas the peak frequency due to first order phase transition had a proportional to t behavior. So the higher the reheating, the higher temperature we have for the first order phase transition, the more separated these two peaks would be. Not only that, there is another problem. If the reheating temperature is anywhere beyond 10 GeV or something like that, as you can see, the peak of the superradiance, the peak of the SGWB due to the superradiance is much higher. It's more than 10 kilohertz. So difficult, if not impossible, to probe with the methods that are proposed. And here, in order to, okay, this is a different alpha again. Here, in order to probe this, in order to construct this curve for the superradiance peak, we have taken the gravitational fine structure constant to be 0.25. And in order to construct this, we have taken the beta upon h to be 9. Now, to show this in a better way, we have considered two benchmark cases. Okay, so the one is the cumulative spectra. I mean, for two different scenarios. One is the reheating temperature 1 GeV. For reheating temperature 1 GeV, we see that the first order phase transition will create a stochastic gravitational background like this. The tail part of it, low frequency tail part of it, can be probably probed in SK in the future if it works like that. And here, for the stochastic gravitational background from the superradiance, we have seen two different curves essentially, because the background due to the superradiance changes depending on what kind of mass we have of the ultralight scalars. If the mass is of the order of 1.5 times 10 power minus 17, I think, then it will be much higher. And it can be seen in, let's say, DESIGO, BBO, Einstein telescope, marginally cosmic explorers, so on and so forth. But if the mass is much lower, which essentially says that the alpha, the gravitational fine structure constant, is much lower, the gravitational background might not be able to be probed by any of these things. Similarly, for the reheating temperature of 0.039 GeV, we have the gravitational wave background for the FOPT, something like this. And for two different particle masses, I have shown the stochastic gravitational background due to the superradiance. So that's pretty much it. Now the point is, there are two situations. Suppose we, in some future observatory, we see this one and we see this one. Now the two possibilities are, the primordial black holes through which this thing is generated had just been there, and this is a separate thing, which is coincidence. I mean, we can only call something coincidence when we do not know the science behind it, but let's say for now it's coincidence. We don't know where these black holes came from of this mass. Or we can consider the fact that these two are the have the same generation mechanism behind that. So obviously, if we see things like this together and we have some sort of other mechanism to measure the abundance of the primordial black holes, which will have a mass so to create this kind of spectra, then we can actually talk in favor of the fact that primordial black holes can actually be created from first order phase transition. If not, then all these things that we all have been doing might have a setback, but let's not go there right now. We are far away from it, I guess. So black hole superradiance can act as a very efficient source of gravitational waves. It can confirm or rule out the mechanism of PVH creation from first order phase transition, or the existence of ultralight scalar of a certain mass, right? One can also consider, so the issue is, we are considering the stochastic gravitational background from superradiance. We can think about transient events as well. Now, if we consider transient events from these superradiance, it can give us monochromatic gravitational wave signals, which also can have memory effects, as we have heard from the talks of Professor Mohanty, Professor Shen, and Orpon. And finally, we have non-standard cosmological scenarios. We can have, the previous talk talked about that for quite a long, which can have initially, so if the collapse is happening in non-standard cosmological scenarios, more precisely softer equation of state, then the primordial black holes can have higher initial spin, which can create, let's say, superradiance, which can take part in superradiance even without any kind of merger, which will give rise to higher gravitational wave background signals. So, yeah, thank you.
Sorry, we're running a bit late, so I'll just take one question. Okay, go ahead. I'll take two questions. Okay.
Okay. So at the first stage of your talk, you were talking about this Carr metric, and this superradiance comes about due to the slowing down of the spin of the that Carr black hole. Mm-hmm. So then to observe this kind of effects, you need to know a priori the spin of those black holes.
Yes.
So my question is how well we can observe these spins. So intrinsic spins, because
the point is, okay, it can be other way around as well. Very few sources are there which can create monochromatic gravitational wave signals. So if you happen to see one monochromatic gravitational wave signal, and somehow you get to know, so the gravitational wave frequency, right, only depends on the mass of the ultralight scalars. So let's say you observe a monochromatic gravitational signal, so you immediately know the mass of the ultralight scalar. So you can know the range of the mass of the black hole also. From that you can get some idea through the equations that I have not shown, the solution of the Tucholsky equation, the spin of the black hole as well. So that can be one way to do the measurement of the black hole spin also. And from the other way around, you can look at the gravitational wave signal, let's say it's merging, and then eventually after the merger, you know initially if the spins were 0, then at the end the spin will be 0.7. So if it's a merger remnant creating the superradiance background, then you know the spin.
So I am actually thinking of independent measurement of the spin of the black hole, and then you check your results. So
independent measurement. So, but then the point is, thankfully we have monochromatic gravitational signals. So if we see superradiance, gravitational wave signal due to superradiance, we will know that these are because of superradiance, because monochromatic signals. Not many things can create that.
Okay,
but
we can
your
discuss.
question is valid.
Yeah. Okay, we can discuss.
Yeah, quickly, please.
Maybe I can ask him later.
Speak up. Speak up, yeah.
So on the plots of the produced gravitational waves, omega GW around the peak looks very high to me, in the sense when you have shown the expression of the probability of the collapse to a primordial black hole, it was exponentially suppressed by beta by h
Yeah, yeah,
square.
yeah.
So what beta by h did you use for your plots? In
Yeah, for zero, we use 9.
Okay. Still you could get like this
Yeah,
10
yeah.
raised to minus 8 and
If beta upon h is anywhere more than 15, then all the papers that I have talked about here, none of them predicts a very good primordial black hole abundance.
all. Okay, thanks.
Let's thank the speaker again. And